All right. Welcome, everyone. My name is, at this point in time, I am Donok, Master Coington. I am the head of the house. Thank you for joining us. This month's seminar is pretty special. It's already our fourth, and it's October. It's my favorite month. It's beautiful outside. And what I'm going to be doing is I'm going to be teaching you guys about a little bit about what I do. I am an aviation meteorologist and dispatcher, so I'm going to show you how I do it and what that's about. I'm sure some of you are like, what is, I thought meteorology is just the dude on the TV. It's a common misconception. For example, whenever I was weather forecaster and meteorologist in the Air Force, I would do stuff for, top secret stuff, in different countries, drone strikes. You could, uh, private aircraft following the cartel. We do, or surveillance aircraft following the cartel. We'd have I did stuff for NASA for their rockets and shuttles, their weather. I did weather for the Army guys, the Golden Parachute team, dropping into NASCAR. We did all kinds of cool stuff. So weather is huge. And then resource protections, WWAs, which is watches, warnings, and advisories for different bases. We wrote all kinds of different stuff. So let me show you guys a little bit about the weather side. So I'm going to assume that I can just switch over. Switch over. How do I share my screen? Is this it? Screen share. There it is. Okay. Share my screen. Oh my god. Sent to everyone. Oh my god. It's getting so intense. I'm sorry, y'all. Okay. I hope that y'all can see this. Because I'm just going to go ahead and do my little bit here and we will see. Okay. So, first thing I do whenever I get to work is I have 4 monitors, but I open these and I'm just going to go ahead and close everything else. I don't have access to a lot of stuff since I'm not at work. But, well, you know what? I can sure try. Let me try to see if I can open up my tunnels and the OIS. Okay. It might work. Maybe. No, it doesn't since I'm not at work on a secure network. All right. Well, basically, this page is just feed straight into air traffic control in the FAA, which is pretty cool. All right. So this right here. Hang on. I just want to make sure that I'm actually still doing a thing. Oh God. Oh, okay. Yeah, you guys totally see my screen, right? Yeah, that's cool. Okay. All right. So this is called COSPA. So typically, whenever I get on shift, I'm going to take a look at the entire CONUS, which CONUS means United States here. And I'm looking, these numbers are representative of cloud top heights typically. So like this means 200, that's 20,000. 240 means 24,000. And I'm really just starting to look here. These are actually indications of cloud temperatures to really tell me what the height is. And typically in the summertime, we're going to see a lot darker decibels like the red, which most people are like, oh, well, that's the thickest of the thunderstorm. No, that's really just the satellite imagery telling us that that's where the coldest tops are. It's going to be higher. And then we can also see live lightning strikes on here as well, which is very helpful for helping aircraft kind of go around, kind of route them around thunderstorms, especially over the Gulf Coast area. So this is a great satellite imagery. Visible satellite imagery is really good for taking a look at. There we go. We can probably, if we go over here to the west, visible imagery is good for seeing overshooting tops. We can see what types of clouds, whether it's alto cumulus, cirrus, if it's a lower stratus, and that tells me the type of cloud tells me how high the cloud is, which is, as you guessed it, important for the pilots. The pilots need to know how high are the clouds. You know, jets like to do certain formations, and they have to have a lot of clear airspace to do specific maneuvers. like 10,000 feet of clear airspace. You can take a look here at Streamline Winds. This shows you pretty much just the general flow. If it flows this way, it's known as cyclonic around a low. If it flows this way, clockwise, it's known as anticyclonic, and that is around a high. And let me just kind of go through and show you what a high and a low really consist of. So you have a high here and a low. This is fantastic. All right, so the low pressure area really shows that it has, it's, I don't know if you guys can see my mouse, but it's basically on the left-hand side here, you have this dipping. It forms a hole in the atmosphere, right? Because it's emptying out and it has upper level divergence and lower level convergence. And this forms the low. On the right hand side, we see the high pressure area. This builds and it's like building an invisible mountain of pressure, right? So that's why a high consists of that. All right. So keeping those in mind, here we have just kind of like a model analysis here. We call this like an LAWC surface analysis chart. So here we can see this is a cold front. We have the active and the inactive section of the cold front kind of connecting down to a low over Texas. Probably have a dry line right through here. If we look at the dew point and the temperature on each side of Texas, it's probably divided through East and West Texas here. But if we look here, this cold front is actually starting to move from the mature stage into the decaying stage because it does have an occlusion. That's what this purple portion is here. This is known as an occlusion when it starts to die and decay. The red portion, as I'm sure many of you know, is the warm front. Now, a lot of times, all right, I'm going to show you how a warm front and cold front works, okay? So warm and cold fronts, how this works is the cold front is known as the bully of the atmosphere, okay? It pushes everything out. See right here where it's starting to push all that warm air up above it and all that moisture on top of that cold, dry air. That's why we get the showers. Now, a warm front is the opposite. It's being shoved on top of another air mass. See, there are lots of different types of air masses. So if we take a look here out over here, we're going to see this is tropical kind of air mass, right? Over the United States, we could have like a continental polar. And over the north, we could possibly have the Arctic air mass, right? Now you get modified. So, of course, so whenever, say, continental polar air starts pushing over Houston, that's modified continental polar air because it's modifying and merging with the subtropical kind of air mass down there. Now, whenever we think of air masses, this is divided up into many different cells in the atmosphere, okay? So when I'm saying cells, I bet a lot of you are wondering, well, what are you talking about? How does this work? Well, the atmosphere around the world is divided into cells. So we have the Hadley cell, your Ferrel cell, and your polar cell. And guess what's in between each of those? Each of these cells is a jet. So we have the Arctic jet, we have the polar jet, and we have the subtropical jet. Now with each of these jets, right? So we'll put air mass. Let me try Hadley cell. I know for a fact if I type in Hadley cell, I'm going to get it. Here we go. So we have, here we go. So here in the mid-latitude cells, we have something called the polar front. These are the westerlies, all right? So the trade winds, this is why weather is inverted in the south of the equator, or the intertropical convergence zone, all right? Now, looking at this, let me try to show you a little bit more about the jets. I'm trying to find something here. Here we go. We have the polar front jet. Now, this jet and the subtropical jet and the Arctic jet, these jets are extremely strong. And it makes it very difficult for pilots to try and fly against the winds, especially with the Coriolis effect, which is the Earth spinning. All right. and you have all of this force of the rotating planet pushing, all right? This is why out over, and these cells get bigger in different sections. Actually, take a look at this. So if you look here at the Hadley cell, see how it's thicker? This means that thunderstorms can get up to 55 to 60, maybe even higher, 1,000 foot for their tops. But over here in the Ferrel, maybe only 40,000 to 35,000. In the polar, you'd be lucky to get 30,000. Very, very short thunderstorms for tops, okay? So that's basically where we're looking at, okay? All right, now, let me go ahead and move on now that you guys have a little bit of the concepts down. I'm going to move along here, and I'm going to close as I go and make room. All right, so we have something called SIGMETs. You have AirMets, SIGMETs. Really? There's no SIGMETs out right now. There's no thunderstorms. It's kind of boring. But basically, they'll put these out for areas of thunderstorms, turbulence, or icing, which is what a lot of pilots care about. All right, so here I can look at something called PIREPs. Now, PIREPs are known as pilot reports. So I'll go to CONUS, and I'm going to take a look here at turbulence, right? So I'll say, okay, well, we got neg means negative reported, light, moderate, severe, and extreme, okay? Extreme means someone's going to die. We have clear air turbulence, wake turbulence. You have just so many different types of turbulence. The runway could have a type of turbulence coming off of it because of the heat. It has enough lift. Like, there's different types, and I don't want to overwhelm you guys. So basically, I can visually see here that there's some quite a bit of turbulence going on here, and I'm willing to bet if there's cloud cover, there's probably going to be icing. So yeah, it looks like there's a little bit of icing. You have rime and clear. Now, and mixed. So what does that mean? What is rime icing, you ask? Okay, well, I'm going to go ahead and show you. Rime icing is basically whenever it's frosted, right? You can't really see through it that well. It's completely like smoky, okay? This is rime icing, all right? Now, see, and this is a diagram of an aircraft wing. And as I said, cloud forms are extremely important to know because, look, this says rime icing and stratiform in the wintertime. So most meteorologists will tell you that, you have your super cooled area is going to be between negative 10 degrees Celsius and negative 20 degrees Celsius, where anytime an aircraft touches water, that water droplet is instantly going to freeze. Now, anything over negative 20 degrees, typically, depending on the area, it can always vary. It's harder for it to be ice. It's just too cold. It's just too cold. But if you have thunderstorms that are well above in the atmosphere where it's negative 20 degrees, you could probably expect lightning. That's called an empirical rule. Okay. Now, as you would think, rime icing is not the worst. It's not. It's not. But I will show you the worst. Mixed is getting worse. Okay. This means it's mixing a little bit with clear ice. So you see the difference here. Rime icing is smoky. Clear is a little bit worse. Mixed, but clear is the absolute worst. Why? It's denser. It's not full of air bubbles. Clear icing is solid, and it weighs a ton. Now, can you kind of think about why that would be a huge problem with an aircraft? Because if especially smaller aircraft, so if you show severe clear icing, right? That is just so bad. That's bad juju. It can weigh an aircraft down to the point where it can't even take off because it's past its weight limit. Its BOW, its basic operating weight, is only going to allow so much, and you have a takeoff limit. You have your structural limit, and as well as possible, like if you're taking out Aspen, you could have obstacle limits, right? And if you can't get up in time at a specific speed, and especially taking into account the fuel load that you have, you might have an issue, all right? So these are different types of icing, all right? So you have trace, barely there, light, moderate, and severe. Okay, so we'll just kind of keep that in mind. And so going back to what I was saying earlier, right? We see the suns here, so we can pretty much expect some icing, but we saw some turbulence, and I see a red one, right? Red, moderate to severe, severe, right? That's not good. So what we're going to do is we're going to go in here and we're going to type in PIREPS. All right, and this is going to take you straight to Aviation Weather Center, and they have an interactive map, right? So I'm going to take a look here. If I have a customer that asks, he's going to say, whoa, I saw it, what does this say? It's luckily pirates are pretty plain text. So UUA means urgent, right? This is the area that they're over right here. The time was at 0045 Zulu, all right, or UTC. Their flight level was 8,000 feet, and their turbulence was severe. Let's see. Yeah. Okay. All right. So they 13,000 and 9,000 feet. They experienced it during descent. Icing moderate clear. So we know that that's clear, clear air, and possible clear icing. Sorry, I just brain froze for a second. Okay, so my first thing is I want to see what kind of aircraft this is. So because looking here, it's not like a Learjet, like a little bitty one. This is an actual general aviation size aircraft. Bombardier, right? Almost the same size as a Gulfstream. So this has me concerned. I would say, whoa, this is a huge problem. All right. And I would tell customers this. I'd be like, hey, avoid this area. We had, an actual CRJ 900 report this. But if it's something like this little guy, like a little Cessna, I'm going to be like, you can handle it. Because it's a smaller aircraft. He can't handle as much. Okay. So now I'm going to go ahead and show you the difference between METARs and TAPs. Now, a METAR is an observed meteorological phenomenon from a sensor, right? And oftentimes they're from ASOS or FMQ 19 sensors. Okay, perfect. Look at that right there. All right, so this is an FMQ 19, right? Oh, look at that. He's Air Force, because Air Force is number one on the leading edge technology on weather systems. All right. This is actually what I used to set up. It's called a TMQ-53. It's a tactical weather deployable unit there. It's about like 150 grand, and it's a piece of junk. But anyway, here we have ASOS. You have from Q19 systems. These things right here, I don't know if you can see my mouse, but if you can't, over on the top right side of the sensor, this shoots the particles between to determine RVR and your runway, whether it's raining or the molecules in the air, whether there's haze, fog, mist. It also has an anemometer, obviously, to tell what the wind speed is and things like that. It has everything, all the bells and whistles. It's very expensive, all right? It's not just like windsock. Obviously there are windsocks on the field, kind of give pilots an idea of what's going on. But this is what spits out this information. Now you're telling me, Corrington, this is just a bunch of gobbly text. Like, what do you want from me? Well, I'm going to go ahead and tell you, all right? So this is called a METAR, and that sensor I just showed you kicks it out. And this tells me, this is over Boston, right? Kilo, and then an IATA is BOS, but an ICAO is KBOS, all right? It's 4 letters. IATAs are not used around the world, just in the United States, pretty much, just BOS. That's why they say, oh, I'm going to go land at LAX. That's because that's just the IATA. Well, the full ICAO of it is KLAX or KBOS, or if you're in, Yokota or Japan or somewhere, it's RJAA or RODN, stuff like that. They have different ICAOs around the world. In fact, I'm going to show you kind of a little bit there. So you have the ICAO codes world. All right. So this shows you around the world what the letters start with. Notice the United States is K, kilo, and it just changes throughout the world. So kind of keep that an idea in the back of your head. All right. So we're going to close these. So this is telling me on the 29th at 0054 Zulu, right? This kicked out at their sensor on the runway. The winds are 240 degrees coming from, right? And at 10 knots, the visibility is 10 statute miles, not nautical miles. And that means that pretty much just unrestricted, 6 miles even, unrestricted, pretty much. Overcast at 037. Now that means 3,700 feet. All right, because that's just this is the tens of thousands, the thousands, and the hundreds. All right, and to kind of give you an idea of how we break this down in the meteorology world, you have few, you have broken, few, scattered, broken, and overcast. Now, this is divided up if you're standing from one point on the surface through the horizon and you look around all the different sectors, you divide it up 8 ways. How much of the sky is actually being used? Taking into account layers too. All right. So this is the chart that we use. If it's clear skies, it's clear. There's few. Scattered, 25% coverage. It's scattered. 75. Now, let's be clear here. If it's here we go. This is a little bit better. All right, 3 to 4, it's scattered. 5 to 7, it's broken. If it's completely covered, then it's overcast. Okay, so let's just kind of keep that in mind. All right. So going back to what I was saying, it's overcast at 3,700 feet. That's where the base of the cloud is. It's 11 degrees Celsius, and the dew point is 5. All right, that's telling me, hey, that's much colder air because the dew point isn't matching the current temperature, which is what it would be if the atmosphere was completely saturated and humid and hot and nasty. The altimeter here is 2979 in inches of mercury, right? And the remarks. This is how I know if it's actually an automated system. A02 means it's automated. Now, if a human being went in here and put AO2 alpha, that means that a person went in, and it's not just the machine. He manually went in. All right. Now, sea level pressure 086 and yada yada. Okay. So next, I'm going to show you a terminal drone aerodrome forecast. It's known as a TAF. I should write these. All right. So this is, and really, it's just playing the category game. So here for Boston, they're saying that this was issued on the 28th at 23:31 Zulu, and it's really not that long ago, right? So, especially if it's about 2Z now, right, for UTC. So that's pretty close. So they say starting on the 29th at 00 is the beginning of the forecast, and the ending is on the 30th at 06 Zulu. So at 00, they're expecting winds are going to be what? Just like the METAR, winds are going to be from 207 degrees at 7 knots, unrestricted biz, overcast at 3,500, right? And then that's going to be effective until the next line, which is 6 Zulu, all right? Broken, 4,000 foot tops. And then at 9, we're showing vicinity showers. Now, civilian TAFs can differ in every country. They can differ between civilian and military. Military's puts the high and lowest temp of the day at the end, as well as altimeter. And that's important because pilots actually change their altimeter on their gauges to be able to land. It tells them, okay. But let's see if we have some more interesting stuff. We got light showers. Oh, here we go. You're wondering, what's the G? Well, the G is gusting. So you have 12 knot winds, but gusting up to 18 knots. So good stuff. So we'll go ahead and move on from there. And so if you're wanting to, wake up and just see what the professionals are saying, the weather wizards with the, storm clouds going around their heads, they usually write a short range discussion here about the whole CONUS area, and they'll kind of give you an idea. Now, all of these things, like these, are known as models. Now, these models ingest very specified parameters and variables into them, and every model looks at different information and computes different things. Now, that being said, when people look at a model, they're like, this is forecasted. Doesn't mean it's the word of God. It just means this model says XYZ while the other one says ABC, okay? So what we will do is say, well, I'm looking at this graph. It means a lot of different things. How do I know if it's even right? Well, I'm going to go. Someone is actually hired to write about, well, how close is the model to real life? Well, they go through every one of these charts. It's their job. And they tell me, oh, well, this one is good or this one is not good. Or the mock is the NAM. So the model consistency is the North American model, okay? So we'll say, oh, well, that's great. Let me see how close it's actually lining up. So I'll go down here and I'll say the NAM. You have NAM, ECM, WF, you have the GFS, UK Met, but I'm a fan of the NAM, all right? And especially CONUS, GFS, everywhere else around the world. So we have actual lines versus forecasted lines. And these are known as contours, all right? Pressure lines. And it's doing pretty well. So I'm just going to say, yeah, I'll use it, okay? So I go to today's date, all right? And we'll say, no, I don't want GFS. I want to go to the North America model, all right? Because I know that's doing well. So I'm going to go ahead and go down. We see here it says Monday, October 29th at 12Z. So this is a 500 millibar relative humidity, right? So you're like, what? Man, you're showing me all kinds of things. It's overwhelming. What's going on here? Well, I'm going to show you what millibars are. I apparently can't spell today. All right, so this is atmospheric pressure, okay? So you have this, all right? So you have your tropopause up at about 40,000 feet, your mesopause, and then your thermosphere, all right? So we're just particularly worried about what's down in the troposphere, in the atmosphere, all right? So that being said, these are millibars. These are your different pressure points. So imagine a giant mountain, especially looking at this, a giant mountain of pressure or a giant dip of pressure in the atmosphere when you look up at the sky, but you can't see it. It's invisible. It's the wind. It's pressure. You can't see that. But that's why, imagine you got winds going all the way up to the top of this warm ridge and then, woo, all the way down to the bottom of the cold trough. Where do you think the bottom of the cold trough is? It's at the surface. That's why you get all these winds just smashing down on you sometimes. It's because the winds, like a roller coaster, they go down and then you get that ground friction and it just hits it, okay? So these are different units of pressure, right? So we're going to go back here and we'll say, okay, well, I don't want to be at this height in the atmosphere because maybe I want to go look at for turbulence potential, right? But 200 millibars is pretty good for this time of year in the winter. You want to look at 300 millibars in the summer. So this is higher up in the atmosphere, right? So 200 millibars, maybe, I don't know, 35, 40,000 foot up in the sky. So I'm looking at this. This is going to show me the wind barbs. Now, I'm going to show you aviation wind barbs. And I hope that I'm still screen sharing because I'm just talking away. All right, so these are your wind barbs, and whatever direction, this is the tail, this is where they're pointing, right? Whatever they're pointing in the orientation is where they're coming from. So notice this one is from 270 degrees. That's where he's coming from, and he's going towards 90 degrees. But look at the actual barb itself. That's a 10-knot barb and a 5-knot barb, so it's 15 knots. This is a 50 knot. So if that's a 50 knot, what is this? We got 10, 10, and 5, right? So it's 75 knots. So with that knowledge now, we're going to go ahead and we're going to look at this. And I can see here clearly that's 100 knots, right? And what do you think that is after talking about the different cells? This is the strongest portion of the winds, right? Well, I'm going to give you another clue. I'm going to go back. I'm going to close this one. And I'm going to use something that's great for looking for dry slots. It's known as the water vapor imagery, right? This is going to show me particularly where there's dry points in the atmosphere here in yellow and where there's a lot of moisture. Dry is right through here, right? And this is the dry slots. Show me where the jet is. Yes, that's right. The jet streams. So with that in mind, this forecast is saying that up here This is the jet stream, the polar front jet curving up. And whenever you have a wind barb that's going one way, but then right next to it's going another, that's probably an indication of turbulence. Or look how we go from 30 knots to boom, over 50, 75 knots. This is an area for turbulence, especially here. All right, so you have directional turbulence or directional shear, and then you also have speed shear, which is the two examples I just told you about. This right here is what we call a jet max, areas of maximum uh, speeds. All right, so I'll show you jet max. Oh boy, PFJ, polar front jet. All right, well, it's not really helping on too terribly much, but whatever. It's basically the idea. So you get United States, and you get the jet going through, and you can have jet fingers trailing up as well. Now, once a cold front starts getting energy from this, oh, it just blows up. It's huge, you know? So this is the turbulence chart. I'm going to go ahead and show you the absolute vorticity. Now, I'm not going to go into like the dry adiabatic and cooling rates and blah, blah, blah. You guys don't need to know all that. But what I will show you is basically lots of red and white, potential for thunderstorms if there's sufficient moisture, if it's the correct air mass. So, being this colder air is pushing down, thunderstorms might be only 30,000 foot, whereas over the East Coast, whereas earlier in the year they were higher, 50,000. It's a different air mass, right? So, just because we have flour doesn't mean we can bake a cake. We also need eggs, milk, we need sugar, icing, we need all the right ingredients for a thunderstorm to happen. So here, we can kind of go through, and this gives us an idea where the most energy in the atmosphere, and that's the best kind of way to explain to non-weather people, okay? You also have to take into account atmospheric conditions, all right, for pilots. Now, that being said, Aurora Borealis, we have some clients that say, I want you to build me a route, and I only want to go, take a flight path that I can see the Aurora Borealis up in my private jet. I spent $60 million on this jet, and I want to do what I want. Okay, cool. We'll do that. We can get a forecast right here. Now, what's also cool about this different website is solar weather is extremely important, okay? I can see here, if there is no coronal or solar flares, that there's very likely not going to be a geomagnetic storm or radiation, okay? That is very important because we have something called HF frequencies for radio and UHF and GPS that all run off of satellite systems. Now, if a proton event goes up, it takes 5.5 minutes for it to move lots of miles across space to get to our atmosphere, and it affects the satellite systems because now you have a satellite in orbit, right? Proton event and a satellite. Ah, crap, I can't spell anything. But all right, you know what? It causes drag is my main point here, okay? So satellites can have drag. Now, what happens when you pull it out of orbit? It's no longer going to be where it's supposed to. It's going to be somewhere else. Now, we have to change how we receive it because it's not in the same place. So that's a problem for not only lots of private companies with satellites, but also we have something called pose and goes. We have polar orbiting satellite systems and geostationary orbiting. All right, that means that it stays in place over certain portions of the atmosphere. So it is extremely important to take into consideration proton events, solar flares, because it's going to affect, if it affects the satellite systems and or even just the radiation, could affect GPS and HF communications, especially if you're going out over the Atlantic or Pacific Ocean and it's a radio and data sparse area and there's nowhere to land. What happens if you have no communications and you can't talk to anyone? That's a problem, okay? And a lot of our pilots will actually call us and ask us about stuff like that, right? So what do? I go ahead. Oh, look at that! It's negative 43 degrees Celsius in Antarctica right now. Oh, I shouldn't have closed that. Hang on. I'll open it. I'll open it. Check it. Oh, hang on. Bookmarks. Oh, here we go. This is the Casey station down in Antarctica right now. I think you guys might just get a kick out of it. Isn't that cool? All right. Anyway. All right. So I'm going to show you. This is some of the products that our clients will call us and ask help with. All right. So there's a lot of rich people. All right. And a lot of rich private companies. You are the cattle and the product, and they reap the rewards, and we give them the weather. It's pretty much how aviation goes. So we have, this is the world low. I'm going to kick on the world high so I can see the airways. All right. I'm not going to go through and explain what all of these things mean. Right. Just assume these things are pretty much airports. Okay. So that being said, there are over 200,000 flights globally a day and very few accidents. So I think we're doing pretty good. Okay. So these are the different airways, right? So what happens when you go out here? It's really data sparse, all right? What are you supposed to do? So we got clients that call in my profession, and we're going to call and don't mind the company. I am not affiliated with this company right now. There's different things that you can give them, like different frequencies, so they can test their equipment, okay? Don't look at that. I'm not affiliated with any companies at this time. Please do not sue me or fire me. Okay. So, and that brings up another point. Whenever you go over different countries, yeah, you're going to need overflight permits, which these millionaires and celebrities that we do stuff for, Justin Bieber, I mean, you name it. I did Katy Perry's tour last year, or no, earlier this year. I think it was her Asia tour. They don't understand that just because you're on a jet, you get to go. They think you can go anytime you want. That's not really the case. It's all government at that point, right? So look, you have to have overflight permits for each of these countries. In fact, some are so unique that it's really complicated. Like China, the Air Force, the Chinese Air Force has to approve you, and you can only do five trips in China. So that's one in, fly around. So you can do, you can fly in, that counts as one. You can do another flight, and then your flight out. 5 flights total. It's very restricted. Philippines, same thing, where it's like once you have to request it well ahead of time. Tell them they need the pilot's documents, the aircraft certifications to prove that it's airworthiness, its certificate. They want to know that the pilots have health inspections. They want to see the passports and all the information on all the passengers. It's very strict. So there's a lot in aviation. I'm sure you guys are like, wow, this dude can talk. It's a lot. I know. I get it. But let's just try some for fun, right? So let's try LAX, right? I want to pull up some airport information. So if I'm a pilot, I might say, oh, well, I just need to know. You guys don't need to know. I'm not going to go through what all this stuff means, but you could go to this website and see the different radio signals, or what you can get your equipment to kind of dial into, the different runway orientations. What is the what is the runway material made out of? Customs going in and out of the country, different countries. We can call them. You can find anything online. You don't need to be associated with a company. You can find this stuff online. All right. But a lot of people, pilots are busy. They don't have time. It's very difficult for them to find the time. Right. So that being said, we have something called ETPs, where if you're going over the North Atlantic, we have North Atlantic tracks, and if you don't have the correct equipment to fly on this highway right here, you have to either go below or above the highway where everyone's at, which most people go above. It goes from 29,000 feet to 41,000 feet, the North Atlantic tracks, and they change every day too, and they're at different heights, east and west. And it's a difficult job for control to get them, staggered like that. But say you go above, so you go 43, 45, whatever, going east or west across, right? You would have to have ETPs, which means you have basically it's just a plan. And here, let me see if I can show you guys something. ETP, all right. That doesn't help at all. Aviation ETP, all right. So ETP, equal time points. Yeah, that's what it is. So I would set up an equal time point. Basically says if something goes wrong in ETOPS too, I would go straight to Keflavik in Iceland. Or if something goes wrong, I'd stop in Shannon in Ireland, right? And then if I'm actually headed to France, maybe I put the last one somewhere in the UK, like Luton. Probably not a good idea to use Luton, but you get what I'm saying. So, and then we have some pilots that I've had some pilots call and be like, "Hey, can I go to Yemen or this country or whatever?" No, do not fly. Some countries are not good. I mean, there are different kinds of fur restrictions here. Kind of show that they have anti ballistic like missiles to shoot down people. So yeah, don't fly. It's there's a lot that goes into aviation. So having to know these things is important whenever someone calls. And lastly, I'm going to finish on something pretty standard called a SKU-T. Okay. So this is something that if a pilot says, "Hey, I want to know specifically. I see some fog outside. I want to know when that fog is going to kick out. And if it does, are we going to get really gusty winds?" Well, if we look at the atmosphere and take a snapshot from the bottom of this graph, it's going to be the surface. The top is all the way up in the atmosphere, right? This is called a SKU-T, right? So the red line indicates your temperature. Green line indicates your dew point. If they go to touch, it's more of a saturated atmosphere. And very likely that you're going to have clouds. If they don't touch, it's drier atmosphere. Okay. So there's very different models here. And you even have a hodograph, but I'm not going to go into the hodograph. That's too old school for me. I like the ones that use thousands of feet. All right. That's just me. Let me see. These are all really primitive ones. Here we go. This is a great one. So these are your isotherms. You have this one doesn't show isodrosotherms, but it does kind of give you the layout. So this is kind of like a bad wind profile here, where it shows the different winds going up through the atmosphere. So we had a SKU-T radiation. Oh, look at that. Radiational inversion SKU-T. Can't beat that. That's quality. All right. So we have an inversion. So what happens if we have, see how the temperature goes out and then goes back to the left, up? Well, that tells me that once the atmosphere reaches this outermost point, this temperature, then all the upper winds, see how above in the atmosphere, it's like 25 knots, and on the surface, it's variable because you got 5, maybe 10 knots. Once the atmosphere reaches, the surface reaches its temperature, the air does, the inversion here is going to break. And all that fast winds is just going to flush all the way down to the surface. We're going to have gusty 25-knot winds. That's why it's normally daytime heating kicks in, and you get gustier winds, and all the fog blows out. Now, there's difference between radiational fog and invection fog, and I'm not going to get into all that, but just want you guys to kind of know that there are some different products out there that we use. So I hope that this has been enlightening. I hope I didn't bore you guys too terribly much. And let me see. Can I unscreen share? How do I stop? Here we go. Hey, it's me again. So, all right, guys. I hope this actually saves. Otherwise, I just talked all this stuff for nothing, and I'm going to be distraught. So, yeah. So, go find us more members, and we can all learn fun new stuff together. So, we need more people. I'll see y'all. FTH.